Okay, well, thank you. Thanks to the organizers. Thanks for coming to the talk where all your questions to omit will be answered. So let me just start off with the definition of I/O. Basically, everything I say today is going to follow from this definition. Amit talked about constructions, so I'm just going to talk about consequences. So an indistinguishability obfuscator is, it's an efficient algorithm that takes as input a program. And it's an efficient algorithm. It preserves the functionality of the program in the sense that the output program has exactly the same input and output behavior as the original one. And it's obfuscating, which in this sense, in the sense of I/O, means that essentially it acts as a pseudo-canonicalizer. Okay? So it provides kind of a pseudo-canonical form for the program in the sense that if you start off with two programs that have exactly the same input-output behavior, and you feed it into this pseudo-canonicalizer, you can't tell which one was obfuscated. So, it's really, the word is obfuscation itself is kind of obfuscatory. You don't really know what it means. So in this case, this is what it means. It just provides a canonical form against efficient adversaries. Okay. So that's the English version. And for the most part, I'm going to be talking about obfuscating circuits, although we'll also address other models of computation. So if you want to do things botanically, which seems to be the theme of this conference, I'll be sitting right here. So we have a let, out on the DIO limb. We have Oded playing in the grass here. We also have Benny, who's, one moment he's working on NC0, one moment he's working on VBB. I don't know where to find Benny. Okay. All right, so I'm going to start off with some simple applications of I/O, just some kind of layups to convince the doubters that I/O is actually interesting, that it can do stuff. All right, so here's a first really great application. So you can prove that an indistinguishability obfuscator is basically as good as any other possible obfuscator. It's the best possible obfuscator. Okay, so Goldwasser and Rothbrum prove that. And the proof is really simple. So, you start off with on the left and the right side with some program. So now imagine you knew the actual best obfuscation algorithm. There was some, really great obfuscation algorithm out there. You happen to know it. Well, you could apply it to that program. But on the right side, let's just, you don't know that best possible, obfuscator, so you just apply some padding to get it up to the same size as the left side. So now if you just wrap indistinguishability obfuscation around these two programs, well, these two programs have the same input-output functionality, so the security definition of I/O says these two things are indistinguishable. So what that means is that, obviously this program is well obfuscated on the left side by the actual best obfuscator. So what that means is that on this side, you're obfuscating just as well, even though initially you only applied some padding, but then you applied this wrapper of indistinguishability obfuscation. Does that make sense?
You're saying ignoring issues of efficiency, this is kind of fine, right? Because presumably this padding, for current obfuscation construction, this padding will be like the size of the universe. So it's, if you don't.
As long as it's polynomial the size of the universe, it's fine with me.
For a second.
I can, yeah. Thank you. Okay, so another application is restricted use software. So,
okay. So the thing that you said before, it only works if the best possible thing is exact, right? Namely, it preserves functionality.
yes. Yes. I mean, maybe there's something you can say about obfuscators that only do so approximately, for whatever approximately means, but what I was referring to was exact, yeah.
Is there, I don't know, should one pad a program before you obfuscate it then to get the properties that this is the best possible obfuscation?
It doesn't seem like that would make much sense to do that, to add useless padding and then apply your I/O on top of that.
Although we do that, right? In all the proofs, many of the proofs are going to tell us about.
Well, I mean, yeah. I mean, for the proofs to go through, I mean, just like the proof for the proof here to go through, yeah, you do actually do that. I'm just saying that when you actually think, what does that accomplish? I mean, I guess it accomplishes something. I mean, certainly in terms of the proof. In the real world, I don't know what that accomplishes. Maybe there's some people that think that there's no difference between the real world and the proofs that we do, but I don't know. Okay, so another sort of easy application is restricted use software. So you start off with this really, pig of a software object, and what you want to do is to create various versions of it. You want to, maybe create a demo version, which is kind of dumbed down. It has fewer functionalities. You want to create multiple tiers of the product that you sell at different prices, and so on and so forth. So writing software is difficult, so if you just actually try to manually remove functionalities from the software, it's not clear that you'll do that very well. You might still leak a lot of what you wanted to hide. Okay, but with I/O you can take a different approach. Instead of sort of laboriously removing the functionality by hand, you can just provide some sort of interface around the program that just sort of screens inputs that you don't want to respond to. Okay. And if this has the same functionality as what you intended, then these are computationally indistinguishable. Okay.
Understand how it solves the problem. For a gaming company, how do you use indistinguishability and ensure them that their software is not going to be stolen?
It's not about stolen. I mean, you're releasing a version of the software. What you want to protect are, I don't know, certain high levels in the game or something like that. And yeah, so I don't know. I'm not a gaming developer, but I'm just saying if there's some way that from the outside you can just sort of screen which inputs you want to respond to, then you can do that using indistinguishability obfuscation.
You should show the last slide again. It's not about hiding what the program does. It's about removing features.
Yeah, so I think this is kind of the confusion that we had yesterday where people were just kind of repeating that it's all about the functionality. So yeah, it's about the functionality, but really what you do in I/O a lot of times is you're removing functionality. You start off with a software program that has originally all sorts of amazing functionality built into it. You have a program with an actual PRF key in it for which you can compute all the PRF values. And then what you want to do is you want to put some wrapper around this and remove the functionality, even though technically that functionality might still be in there somewhere in some sense. It's really about removing functionality and protecting secrets by doing that.
So one of the things which, I know about, these applications and, solving all the problems in crypto, but one of the things, at least initially when people talk about maybe obfuscation, especially if obfuscation is efficient, so you have like super fast implementation of something, your competitors are much slower, and, you don't want to use the code, you want people to use your fast thing without knowing what it is, so that's your competitive advantage, speed. So is there any way, either this obfuscation or something, in the future could address this particular concern that you want to hide how you got something that fast?
Hide something?
Implementation that you got really fast.
Oh, you want to say that you have an implementation that does something really fast and you want to demo that?
Some problem. I managed to get something, and my thing is like faster than every competitor in the market. And without going to courts or whatever, I want to let people use my fast thing, but without competitors to just stealing it. Aside from obviously using my thing, which kind of says my name on the cover or something like that. So I really want to, what I want to protect is the secret how I got something really fast, right? And the current definition say any programs with the same size or any circuits of the same size. So is there any hope, some format?
I don't see how to do that using just obfuscation. I mean, you might try some other technique like proofs, but
Presumably, for example, if obfuscation only adds doesn't add that much overhead, what you would do, you would get your fast thing and add a little bit of obfuscation, it would still faster than competitors
Sure.
do it. But it doesn't seem to address this kind of application.
sure. Yeah. So if at some point we get amazing obfuscation schemes, then you could do that amazingly efficient. But
No, but I'm saying
for the moment,
assume you have some really fast obfuscation. Assume you guys solve this thing. You have amazingly fast obfuscation. I still don't see how obfuscation can solve my application. So assume you have something amazingly fast. I mean, how are you going to use a theory of obfuscation to actually provably say that you're going to protect, right? Because I mean, let's say IO just says any two programs which are equally slow, you're not going to tell. Here, I mean, there is no other program which is equally slow. I'm like the fastest guy in the market. So how am I going to protect my? Do you see what I'm saying?
not exactly. No. Yeah, I mean, IO always starts with two programs, and what you want to say is that the obfuscations of them are indistinguishable, and you're saying that you have one super fast one, and maybe there's nothing else that's super fast. I guess I haven't really thought about that situation. Yeah, so I don't know the answer.
You think of the running time as part of the output, typically. Like if another program runs slower, then it doesn't have the same.
Make the leap of faith that it works.
Okay, so another pretty easy application of I/O is witness encryption. So the idea in witness encryption is that you want to encrypt some message so that, say, only someone with a proof of the Riemann hypothesis can decrypt it. Okay, so so more formally, you encrypt a message relative to some statement, and you can decrypt it if you happen to have a witness for that statement. So there's no real secret key in the system per se. It's just that if you happen to have a witness for that statement, then you can decrypt. Okay, and what we want in terms of security is that encryptions of M0 and M1 are indistinguishable if it's the case that the statement is not in the language. So here's how we create it from I/O. You start off with a program that does sort of what you would expect. It gets as input a purported witness, and it will output the message M if W is in fact a witness for the statement X. Otherwise, it'll output bot. So consider that program, and you put I/O around it, of course. That's going to be your big ciphertext. So you just feed your witness into it, and out pops the message if it's valid. On the right side, you have a program that always outputs bot. Okay, you I/O that. These two things are computationally indistinguishable if it's the case that the X is not in the language, right? Because there's no satisfying witness. So that's how you prove the security of the witness encryption scheme. Okay, we just wanted that if X is not in the language, that encryptions of M0 and M1 are indistinguishable. Okay, no real guarantees if it happens to be the case that X is in the language. So, clear?
But why would you want to do that? I kind of understand the technical part, but why? What does it give you? What's good about it? Like, I'm asking the application, I guess. What's?
I don't know. Maybe you want to encrypt, a bank account number or something. If someone, solves Riemann hypothesis or something like that.
What is the language that X is in the language or not?
I mean, you just have a language that verifies the proof of. You have to write the proof in some formal language. It verifies it, and if it's true, then it gives the message.
Well, I guess maybe Talid's asking, let's say we encrypt under something we believe is true, we just care about the proof, like P not equal to NP or something like that. So here, if everybody believes it's true, you can just put identity function and it will satisfy your definition. So it's like it doesn't address the things that you really need to know the proof, I guess. Maybe that's what Talid's asking, I don't know, I'm guessing.
Yeah.
So it doesn't address the things that you really know the proof. Let's say if everybody knows X in the language, you can just put identity function or something.
Yeah, so it doesn't work for that situation, but
I mean, formally,
For something you have more doubt about it, it's interesting.
Languages telling membership is a hard problem.
Yeah.
Then,
Yeah, so that has lots of applications. I mean, it's not for statements that we believe are true. It's probably not for these. Yeah. Okay. So all of the above applications are maybe a little uninteresting in the sense that they have relative security. So for best possible obfuscation, all I could say is that the obfuscation is as good as any other. For restricted use software, it's, depends on the quality of the restricted interface that you wrap around the program. For witness encryption, there's no guarantee when X is in the language. So obviously, we want to create crypto systems that have sort of more absolute guarantees. And to get that, we typically need to make an additional assumption, like the existence of one-way functions. You would kind of think that I/O being an extremely powerful object, that it already implies one-way functions. Not exactly. So as Amit said yesterday, if P equals NP, then indistinguishability obfuscation exists. Just because it's easy to provide a canonical form to your program. You just provide the first program lexicographically that provides that functionality. Okay. So it doesn't just straight out imply one-way functions. But there is this result that I/O implies one-way functions if what we think is true, that NP is not in BPP. And the proof is pretty simple. What am I going to make my one-way function? Well, just the obfuscation algorithm. Okay, so my one-way function f of x is going to be an I/O obfuscation of some program z that's just unsatisfiable everywhere. It's just a program that always outputs bot, right? And x is sort of the randomness that I provide in the obfuscation algorithm. Okay, so I'm just again, f of x is just an I/O obfuscation of this fixed program z. The randomness I use in the obfuscation is the input x. Okay. So why is that a one-way function? Well, first of all, imagine a world where I switch z with a circuit that is also unsatisfiable. Well, then I/O says that I can't distinguish between these two worlds. And so if an adversary can invert the one-way function here, it should be able to invert the one-way function here. Of course, it's still going to invert with respect to z, because that's what it's supposed to do. Okay. So the adversary will still be successful here, because these two worlds should be indistinguishable by I/O. C1 and Z have the same functionality. So now imagine that instead I put a circuit in there that is satisfiable. Well, then the adversary can't invert, because there doesn't exist any x such that this y2 here is an obfuscation of C2. Because the set of obfuscations of C2 is just disjoint from the set of obfuscations of Z, because they have different functionalities. Okay? So this gives me a way to tell whether a circuit C is satisfiable or not. I just feed it to this inverter, and depending on its success or not, he'll tell me whether it's satisfiable or not. Okay, so that proves the claim.
Does this extend to non-perfect functionality? Going back to
what do you mean by non-perfect?
So it could be that the obfuscations of C1 and C2 have some tiny, tiny intersection, very low probability. The obfuscator doesn't preserve functionality.
This proof, again, there might be some way to extend it to this case, but what I'm talking about here is perfect.
They extend it. In the paper, they have a slightly different construction.
Okay. There are probably going to be lots of cases like this where, there are about 100 papers on applications of obfuscation. I'm not going to know all the details. So just, shout out if you happen to know the answer to some question. Okay. All right. So now I'm going to give you another simple application, which is a way to get public key encryption from witness encryption. Okay. The scheme is pretty simple. The public key is just going to be the output of a PRG on some secret key. Okay. So this is like the world's fastest key generation algorithm for a public key encryption scheme. I just use a PRG. It's length doubling. Okay, so I'm going to use an encryption scheme. I'm going to use my witness encryption, and I'm just going to encrypt relative to the statement that there exists some pre-image of this public key for the PRG. And to decrypt, well, I have my witness, which is the seed. How do I prove the security of this? Well, first of all, I have my encryption of M0, where the statement is with respect to the actual public key. Now I'm going to switch the public key to just be a perfectly uniform string. You can't tell the difference by PRG security. Here, there's probably, if this is a perfectly random string, there's probably no pre-image with respect to the PRG. So it's unsatisfiable. So I can replace my encryption of M0 with M1 by witness encryption security, and then finally I just go back using PRG security, back to my valid public key. Okay, so that's it.
So we didn't even need I/O here. I mean, it gives us a way to construct one of my functions in witness encryption, but like, it's not necessary if we have a witness encryption scheme and a...
Yes. Yeah, this is just from witness encryption. Okay. So there are other cool applications of just witness encryption, like identity-based encryption, attribute-based encryption for circuits, secret sharing for monotone NP access structures, and so on. Okay, so those were kind of the layup applications, and now I'm going to get into kind of techniques, how we use I/O in security proofs to prove the security of more complicated objects. Okay, and there are sort of two main techniques. One I'll call shell games of secrets, and another is punctured programs. Yes?
Sorry, can you go back to the last slide? What is a monotone NP access? Sorry, I don't know.
It's some... it's complicated. So it's basically, so you have a monotone function, f, and basically every string that satisfies this monotone function f corresponds to a set of players that should be able to recover the shared secret. So you have a string with zeros and ones. You look at the guys. I mean, this is an n-bit string. There are n players. If the guys corresponding to the ones in this string, they should be able to combine their shares to get the secret. All right. So shell games with secrets. Okay. So here's kind of a thought experiment. I like to have these deep thought moments, kind of like, can a mind understand itself, that sort of thing. So, so here's kind of a thought experiment. So imagine that you have some program P1 that uses a secret key SK1, but there's some totally independent secret SK2 that it doesn't use, it doesn't contain, it doesn't know about, right? And on the right, you have the flip side. There's some program P2 that has SK2, but it doesn't know anything about SK1. But for some reason, these programs are completely functionally equivalent. So, so that means that if you put I/O around them, they should be computationally indistinguishable. So my question is, does either obfuscation reveal the secret key SK1 or SK2? Okay. Answer is no, of course. So you can clearly see that P1 hides SK2 because it's not there. And the flip is true. But on the other hand, by I/O, the two programs are computationally indistinguishable. So we can say that P1 also hides SK1 because it's, it's similar to P2, the obfuscation of P2. So this is the two-key technique of Noah and Young. And it just shows that both secrets are hidden. Then you might complain that, well, okay, that's kind of silly. I mean, you have a secret key that's not used. What does that mean? What can you do with this concept that seems kind of useless? turns out it's not so useless. So before I get into how it's used, let me first remind you about FHE, because I'm going to use it here in a second. So fully homomorphic encryption. So you have some data that's unencrypted. And you might have a circuit that's unencrypted, and obviously you can evaluate the circuit on the data. It might be the case that the data is encrypted with an FHE scheme, or even that the circuit is encrypted with an FHE scheme. And what you can do with the FHE scheme is that you can evaluate that circuit on the encrypted data, and you get an encryption of C of X. You can have other variants of this. You can evaluate an encrypted circuit on encrypted data using the universal circuit. You still get C of X, an encryption of C of X. You can evaluate the encrypted program on the unencrypted data. Same thing. Okay, so really what I wanted to get to is that in the next slide we're going to use an encrypted program that we're going to evaluate on unencrypted data. Okay, so this is one of the promises that I have to fulfill for Emit of describing, how do you bootstrap I/O for NC1 circuits to I/O for general circuits. So this is what we're doing here, and so. Current FHE schemes have decryption algorithms that are in NC1. Okay, so here's, I'll describe to you what the obfuscation of the general circuit is going to be. So I have some general circuit C. What I'm going to do is I'm going to, first of all, encrypt C under FHE public key PK1. I'm going to encrypt it again under PK2. And then I'm going to provide a gnarly obfuscation, which is sort of a conditional decryption algorithm. What does it do exactly? Well, it takes as input some value x and a couple of ciphertexts and a proof. And what it does is it has hardwired the encryptions of these two original circuits. And what the proof is supposed to prove is that what I did to get C1 is that I evaluated this first encrypted circuit on the input X. And what I did to get C2 is I evaluated the second encrypted program on X. Okay, the proof should prove that. And if that is in fact the case, that all the steps, I did all the steps correctly to get these ciphertexts, then it'll output the decryption of the first ciphertext under SK1. Otherwise, it outputs POP because it's unhappy. Does that make sense? So, if I jump through all the hoops and I actually did what I was supposed to compute these two ciphertexts, then it really should be the case that the first ciphertext encrypts C of X under PK1. The second ciphertext encrypts C of X under PK2. Right? If the proof verifies, this is an actual proof, it's not an argument. If the proof verifies, then that should actually be true, that these are encryptions of the same value. Yeah?
Does the proof include C1 and C2?
No, the proof doesn't really have, it's just kind of the proof can be like a transcript of the whole computation that's used to. If you like. Yeah, I didn't say it doesn't include it. You can go ahead and include it. It's just going to be a long transcript of the entire computation that's used to derive C1 and C2 from the original ciphertext.
And your program takes C1 and C2 as input just for convenience?
You're proving a statement about C1 and C2.
He's saying, why didn't you write C1 and C2 since it's already implied?
You're asking about the little C1 and C2, right?
Yeah.
Well, it's just that it's much faster or shallower to verify this statement than to actually run the computation yourself. This is the thing that you're going to use later.
Yeah, I guess I could just have the proof included, and yeah, you're just. I think I'm missing your point, but. Yeah, so it's going to be a really long proof because it's going to be basically as long as the entire homomorphic computation. But the point is that this proof is can be very shallow. Like basically you express the entire computation as a circuit, say, and you have to prove that for each gate I computed it correctly. And so you have different blobs in the proof for each gate, and you check that the wires between the gates are consistent, and all of this can be verified by an NC1 circuit in very shallow depth.
So I'm just confused. So ISA by is encryption under PKI of C or the message? Sorry, I'm confused. So what is C? There is C, C1, and C2. There are C.
Okay. Yes. Yeah, this is a big C, sorry.
Okay.
I guess that's an issue. Okay. So, everything here can be done in NC1, verifying the proof and doing the FHE decryption. So we can use our IO obfuscator for NC1.
So why is it clear that this is NC1? Because it just, well, I mean, it's obvious you need to use the property of, what do you use here?
You just, I mean, you express this entire computation as just gates. You have little blobs in your proof for each gate, and you prove that all the gates are performed correctly, that all the wires in between the adjoining gates are consistent. It's all highly parallel.
And because decryption is parallel for FHE.
Yeah. Yeah, so all this can be done in NC1. Okay. So one thing I want to point out about this program is that it doesn't have SK2. It just decrypts the first cipher. After verifying the proof, it just says, okay, now I'm just going to look at the first ciphertext and decrypt it with SK1. Okay. So this is what we have in the real world, and I've just sort of highlighted the SK1 and ciphertext 1 aspect of it. Now, if you imagine a different world where instead the conditional decryption algorithm had SK2 and decrypted the second ciphertext with that, well, I claim that these two programs have completely exactly the same functionality. Because either the proof verifies or it doesn't, okay? I mean, if it doesn't, the output's bought. That's the same in both cases. If it does, then it's actually the case that the two ciphertexts, C1 and C2, encrypt the same exact value. So they have the same exact output in that case also. All right. Yeah, so by the previous argument, I can at least prove here that, so there's a program here that uses SK1, it doesn't know about SK2, and then the flip side, and they're computationally indistinguishable. So I can at least say at this point that these programs hide SK1 and SK2, but that's not really what I want to prove, right? I want to prove that I have an indistinguishability obfuscation scheme for circuits, which really has more to do with the encryptions that I provide of the circuits, rather than the particular secret keys. So, but I want to kind of bootstrap this fact to prove that I get I/O.
Correct. So, okay, it doesn't contain SK whatever over index, but it contains a public key in a way in the proof, and the public key is like created from the secret key. So why should it hide anything in a way?
Let's just go over the proof, and so yeah, so you'll see there. Okay, so here's the proof. Suppose you have two circuits, C1, C2, with the same functionality. All right, so I'm going to create a few hybrids. Oh, God, what happened here? Okay, so wherever all these down arrows are, those are subscripts, okay? So like this is like a hybrid subscript circuit, and then bet B1, okay? So at least the arrow has some connection to subscripts. I'm a little afraid of what will happen later. Let's see. Oh, God, this is horrible. Huh?
Craig, do you want to use
I'll just, let me try to go with it here. Okay, I'll describe it in words, so you can mainly focus on my words. Okay, So what we have over here is an IO obfuscation of C1. Okay? What that means is that that both of the encryptions, the FHE encryptions, encrypt the circuit C1. Okay? And inside the obfuscation, I use the key SK1. And over here, I have an IO of C2. So that means both of the encryptions encrypt C2. And still SK1 is used, because that's just the, SK1 is used in the obfuscation. Okay, so I want to get from there to there. All right. So, so here to respond to your question, so when I'm in the first hybrid, what I'm going to do is I'm going to change what is encrypted under public key 2. In this world, only SK1 exists. We don't know anything about secret key 2, so we can say that the semantic security of the encryption scheme, I can change what's encrypted under public key 2. So what I'm going to change it to is circuit 2. So now circuit 2 is encrypted under PK2. Okay. Next, I'm going to change the secret key that's used inside the obfuscation. Okay. So both of these circuits have the same functionality, so I can say that the same result is going to be decrypted. I get the same encryptions of the same values under public key 1 and public key 2, so if I switch to secret key 2, the functionality doesn't change, and IO says that this is indistinguishable. And then I keep going like that. So next, at this point, secret key 1 is nowhere to be seen, so I can change what's encrypted under public key 1, and I change that now to circuit 2. And then finally, I do one more IO. I switch the secret key under which you decrypt, because it doesn't change the functionality, so by IO security, this is also indistinguishable. Okay. So that's kind of how the shell games of secret technique is used. You kind of go back and forth between using different secret keys and changing other parts of the program, and eventually you're able to traverse your way over to where you want to go.
Can you show for a minute the construction in the previous one?
Yeah, this isn't exactly what I was proving. I mean, I just wanted to, first of all, give you some intuition that at least secret key 1 and secret key 2 are hidden. And then this fact is sort of kind of leveraged to...
I guess the step I didn't understand is the first I/O security. Like, why is it the same functionality in the next, like the first, this one? Why is it the same functionality? You decrypt the second part, no?
Yeah, so these two circuits have exactly the same functionality.
Yes, okay.
And so what you get at the end, the final encryption, after you evaluate the FHE, it's still the same thing. Okay, so that was bootstrapping IO for NC1 to IO for circuits. I do have one more slide that's going to have some these arrows in it. Hopefully there aren't too many problems. Okay.
Give me your thing, I'll put it on mine.
That's okay.
In case it gets really bad.
So what type of proof do you have to use?
Huh?
What type of proof? How do you construct phi?
It's just it doesn't have to have any zero knowledge properties. It's just a real actual proof. So you just lay out the entire computation that you did, express it, as I said, in terms of a circuit, in terms of gates. It's just a real proof, and you feed that whole thing, the whole transcript of the computation into that obfuscation, and it's able to verify it in a parallel sort of way. That's sort of the key. Okay, so another application of this shell games is functional encryption. So the idea in functional encryption is that you have some authority who generates a master public key and secret key. And this authority is able to distribute keys for functions. Okay, so F1 is a function, F2 is a function. For some reason, these receivers are entitled to get secret keys for these functions. These functions might describe the policy under which that particular user is allowed to decrypt, for example. Or it might describe some sort of redaction function for that particular user. Then some sender comes along and uses the master public key to create a ciphertext that encrypts some value x. And what the receiver should get are their particular functions of that x. Okay. Sometimes it's nice to look at it as sort of a delegation scheme or to kind of compare it to fully homomorphic encryption. So in the cloud scenario in fully homomorphic encryption, you like to send your encrypted data. The cloud can compute whatever function it likes on your encrypted data and send it back to you. In functional encryption, the cloud or whatever is sort of committed to this particular function that it can compute on your data, and then it could send that back to you. Okay, so to define security, the selective version of the game is that the adversary selects some 2 messages. The challenger creates the public key and some challenge ciphertext. And the adversary can make key queries subject to this obvious constraint, because if he asked key queries that didn't satisfy this, it would allow him to easily distinguish what was encrypted. Okay. So the adversary can make key queries like that, and finally the adversary guesses what was encrypted. Okay, so how do you get functional encryption from I/O? So first of all, you create some just public key, no FHE here, PKE pairs, PK1, and so forth. And then you have a CRS for a special type of proof, which I'm not going to describe at the moment. I might say a little more about it later. And then the encryption scheme is kind of similar to before. When I encrypt X, I doubly encrypt it under the 2 public keys, and I provide a proof that I encrypted the same value under the 2 keys. And then the decryption key for F is just something that it gets as input the cipher, the double ciphertext, and the proof. It checks that these 2 things indeed encrypt the same value. And if that's the case, then it decrypts the result, applies the function f, and outputs. Okay, so yeah, here, okay. Boy. Yeah, well, no. All right. Okay, so what sort of hybrids are we going to have? We're going to, basically do the same sort of thing. We're going to use I/O security to change the secret key that's used inside the obfuscation. And we're going to use semantic security to change what is encrypted here. So we're actually going to have hybrids where X1 is encrypted here and X2 is encrypted here, for example. And the reason that I need this crazy proof is that in the hybrids, I'm going to prove something that's not true. I'm going to prove that these 2 things encrypt the same value. It's just that this is a special proof that provides an escape hatch for the particular ciphertext that I've created in these hybrids, the particular challenge ciphertext. Okay? So this proof allows me to prove only true statements, except for this one statement that I want to fudge on. And this type of proof is indistinguishable from a proof that just doesn't allow that sort of escape hatch. So really the proof is sort of exactly the same, except for that aspect. I have this alternation between using PKE security and I/O security. This would be exactly the same as before, except that when I try to use I/O security, I'm in fact encrypting different values here, x1 and x2, and so I can't actually provide a real proof that these two things encrypt the same value. So what I need to do is I need to use this statistically simulation sound proof to go to a world that has a proof system that allows that one escape hatch that I want to use in these hybrids. And then I just do the same thing as before. Okay, so where I'm encrypting different values here, the proof system makes an exception for that case and allows me to pass. And then once that's the case, I mean, I can do a proof, and I/O security holds here, because the functions because in the selective security game for the functional encryption scheme, I can only make queries that evaluate to the same thing on the two messages. And so even though these are different messages, the output will always be the same. Does that make sense?
Wait, but on the previous thing, which hybrid doesn't work again? I just want to make sure which hybrid doesn't work.
So if this were an absolute proof system, where I'm supposed to be proving that I'm encrypting the same values under the two different public keys, I wouldn't be able to provide a proof here, because in this hybrid I'm actually encrypting x1 under the first public key and x2 under the second. So I use this crazy proof system that allows me to create a fake proof for the particular challenge ciphertext that I'm creating at that point in the proof.
So some of the functionality is preserved now with the simulation sound proofs. It is preserved because you're saying the proof is actually incorrect on some proof. It's correct,
but no, the proof is incorrect, but the two x's do have the same output value under f, which is...
Oh, I see. That's the point. So they have the same value.
Yeah, so when I switch keys, I decrypt x1 over here. If I use this secret key, I decrypt x2 over here. If I use this secret key in the next hybrid. But in the functional encryption security game, I'm only allowed to make key queries on functions that are consistent, that have the same evaluation on the two messages, and so the output of the decryption will be the same. Okay, so that was kind of the playing shell games with secrets technique, and now I want to go over punctured programs. Okay. So I have to admit that the punctured programs technique is probably a little more useful than the shell games of secrets one. It's been used a million times over. So what is a punctured program? So I'm just going to say that this PT is a punctured program at T. If it's, it just evaluates as the same thing at P everywhere except T, where it just outputs bot, which means undefined. And basically, the idea of the punctured programming strategy is that, first of all, I want to try to show somehow, I'm being very vague here, but the general strategy is that I want to prove that these two programs, perhaps if this is a component in some outer program, that the overall programs maybe have the same exact functionality, and therefore the IOs of them are indistinguishable. And then I want to also show that the adversary needs P of T to win the game, but he can't get it in this case because it's punctured at T. So Sahai and Waters have a sort of nice description of it. So the idea is to alter a program, which is to be obfuscated by surgically removing a key element of the program without which the adversary cannot win the security game, but in a way that does not alter the functionality of the program. All right. So kind of the key punctured program that we'll be using over and over again is the punctured PRF. Okay, this is the punctured PRF. If it's punctured at T, I can give you a key KT that allows you to evaluate the PRF everywhere but T. Okay, And moreover, if I give you that key, it should even be pseudorandom at the value t. Okay. It's pretty easy to create punctured PRFs even from GGM. So you all know and love GGM. Gosh.
You want the laptop?
Yes. Okay. It's obviously a superscript, but
It's obfuscated. These obfuscators, that's so good. You told us this. I'm sure you can guess it yourself.
close enough. All right, so you all know and love GGM. So you have a length doubling PRG, which, given some seed, it outputs G0 of R and G1 of R. And then basically the PRF on some string X is that you just go left or right down this binary tree defined by this PRG, depending on the bit of X, right? So now I want to puncture the PRF so that the user can't evaluate the PRF at this particular value at t. What I do is I just provide enough material from the binary tree that allows the person to evaluate everything else. So I give the user this value. After that, he can evaluate this whole subtree of the PRF. I give him that value, all the one-off values, and then using those, it's only logarithmic in size. This is basically k sub t. Okay, it's not pretty nice and compact. Can evaluate everywhere except t. Okay, so now I want to create public key encryption using punctured PRFs. I already described public key encryption from I/O and one-way functions before, from witness encryption. But it wasn't really what we intuitively would like to do. So Diffie and Hellman sort of described sort of what you would ideally like to do is just obfuscate the encryption algorithm. Take a symmetric cipher, obfuscate the encryption algorithm, provide that obfuscation as the public key. Anybody can encrypt, but for some reason people can't decrypt. Okay, the secret key is hidden. If you just add enough, dummy variables, blah blah blah, maybe that works. Okay. So, for example, let's take a stream cipher. Okay. You could try to do that, but you would not be successful because a stream cipher encryption is its own inverse. So that's not going to work. So if you provide an encryption encryption and decryption are the same exact algorithm, right? Okay, so it doesn't work in that case, but let's just change the stream cipher just a little bit. So instead of outputting R here, I'm going to output PRG of R, and I'm putting G applied to R here also. And so obviously you decrypt by taking that, applying the PRF to that, getting the message. Okay, so obviously it's kind of harder to go in the reverse direction once you've applied this PRG to there. And this is the Sahai Waters actual scheme. So this is it. This is the public key encryption scheme. So it has this one has super fast decryption. Okay, so it's just basically the evaluation of a PRF. Okay. Now I'm going to prove security.
Just for a second. Show the previous thing that doesn't work. You didn't use punctured PRF. You just use regular PRFs.
It doesn't matter what you use here because encryption and decryption are exactly the same algorithm. So if I provide you an obfuscation of the encryption algorithm, that's you can also use that to decrypt. So
you fix it in two ways. You put G of R instead of R, and somehow you made this sneaky move to punctured PRF.
Oh, yeah, okay. I made a sneaky move also. Yes.
And where do you puncture the sneaky thing at G of R? Or?
Well, allow me to tell the story. Okay, so now I'm going to prove security. All right, so here's the ciphertext, right? So I have this, I have this value here which is just a PRG of some randomness. Okay, so this is my ciphertext, right? So it's the PRG of some randomness, and then it's just the PRF evaluated at that initial seed. And then XOR of the message. Okay, so that's the ciphertext. First step, this should look pretty, I guess, familiar. First step is just to make T uniform, PRG security. Okay, so now it's uniform. Okay, so now kind of like before, it's probably not the case that T is in the image of the PRF. Almost certainly it's not the case. Okay, so this PPRF here is never going to evaluate on this new T, because it's just not in the image of G. Okay, so I can, without changing the functionality of the program, I can puncture the PRF at T, because it's never going to evaluate it there. And yeah, so instead of, and everything's the same, I just use this punctured PRF key inside there. Does that make sense? And so that's indistinguishable by IO security because I didn't change the functionality with overwhelming probability. Okay. So now I've done that. Well, by the punctured PRF security, I can replace. So I still have this value in the ciphertext. See, I mean, I still put this value in the ciphertext. It's not inside the obfuscation anymore, but it's still the case that this challenge ciphertext is masked by the PRF value evaluated at T. So now I just want to replace that with something completely random. So I can do that because punctured PRF security says that this just looks completely random if I only have a punctured key. Okay. So now everything's just random. So that's it. Make sense? So that was punctured PRFs. Another technique I want to talk about is complexity leveraging. This is often used in proofs. So the strategy is that typically you start off with a scheme for which you can prove selective security. So you try to guess which input the adversary will in some sense attack, which input. Okay? And if you happen to be correct, then in that case, you'll be able to prove that you can use the adversary to break IO or the punctured PRF security. Okay, so in other words, the adversary and the adversary's advantage in the selective game is less than its advantage in the IO plus punctured PRF games. Okay. But in a lot of cases, of course, I want to prove adaptive security. I don't want to force the adversary to commit to some particular value to attack beforehand. So what do? Well, I just try to guess which value, if I'm the challenger, which value the adversary will target. I'm correct with probability, 1 over 2 to the n, or 2 to the k, right? And so in that case, I can show that if you look at the adversary's advantage in the adaptive game, that basically its relationship to the selective game is that the 2 to the k difference loss factor there, right? Because I guessed. Okay, so in other words, the adversary's advantage in the adaptive game is less than 2 to the k times some stuff related to I/O or the punctured PRF, say. Okay. And then you just you boost up the security parameter until this 2 to the k doesn't matter anymore. So if you have incredibly strong I/O and punctured PRF security, this 2 to the k doesn't matter, and the adversary's advantage in the adaptive game is negligible. Does that make sense? So if you look at the PRF, for example, so the number of possible inputs to the punctured PRF is really small. Say it's only 10 bits. You can definitely amp up the security of the PRF so that you get as much security as you want, even though because the security is related to the size of the key, not the size of the input. So you can just boost up the security as much as you want. And then I/O also, you can just sort of boost the parameters of the scheme so that it dwarfs the size of the input. Okay. So intuitively, yeah, you kind of try to get security at one point, and you just use this argument to say that you get security at basically all points that you care about. So okay, so for example, you can get a constrained PRF. So I described a punctured PRF to you that was punctured at one point, but let's suppose that I want a PRF such that I can give some key, k sub c, that allows someone to evaluate the PRF at all x for which c of x is 1, where c is arbitrary. And for all unsatisfying x, you want the punctured PRF property that it looks pseudorandom. So, I mean, we can't just, puncture, 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 because there are an exponential number of points that we want to eliminate. That wouldn't be efficient. Okay, so what we do instead is we just provide an I/O of this program, which if c of x is 0, output bot, else output the PRF value. Okay.
Should that be PRF, or what is PRF? Punctured?
Punctured.
But it could be the regular PRF.
Well, we use the if you believe in proofs, you should probably you should use the punctured PRF because that's going to be we're still going to puncture the PRF in the proof.
I have a more general question. So the PRF, the punctured part, comes in the proof or already in the construction? Because in the construction, what's the difference if I just use the PRF? And then in the proof, I will plug in the PRF. No?
It needs to be the same PRF, I guess. So it needs to have the property of being puncturable.
You can't use any PRF. You need to use one.
Yeah.
Oh, you mean I need to use a puncturable PRF?
Yes.
Okay, but it's not already punctured. Like in the construction, it's a PRF if the puncturing happens in the proof, right?
Yeah, the puncturing just happens in the proof, but it has to be a PRF in the real scheme that has the property that in the proof you can puncture it. Yeah.
GGM is good.
Yeah, so GGM is good.
Although, if you're going to use AES and your scheme will become insecure, then you get a proof that AES is not punctured, which sounds like something weird, right?
Yeah, that would be interesting. But on the other hand, I have no idea how you would puncture AES, so it seems kind of hard.
I'm not saying you can, but
yeah.
Getting a proof that AES is not puncturable sounds like a strange thing.
Sure. Okay. So how am I going to prove the security of this thing? Well, let's suppose that I pick a random t such that t just evaluates to 0. Okay. Let's just assume that I can do that. It might be a very sparse set, but you can artificially boost it so that it's not a sparse set. And so let's just say that I can sample some random t such that it's unsatisfying. Well, then the obfuscations of these two things should be indistinguishable. One, it's unpunctured, and here it's punctured at t. Okay. So if I look over here, I mean, there's nothing about T over here. So I mean, you know, the adversary is going to pick some value to forge on. You know, there's nothing about T here. So with probability 1 over 2 to the n, it's going to pick the actual T that we care about. Right. So I divide by 2 to the n, and these two things are indistinguishable up to this epsilon IO factor. Okay, so that means in this world also, the adversary picks T with some noticeable probability. Okay, and if he does in fact pick this value and he outputs the evaluation of the PRF at this particular T, then I've broken PPRF security. So yeah, I should probably find some point to stop. I might go a few more minutes. Okay. So you can do not only constrained PRFs, but constrained signatures. Basically, the signature looks exactly like a constraint at T looks like a constrained PRF at T. You just have to provide some verification algorithm for it. So you just want the property that for all x that are satisfying, you can use this box to sign that value, otherwise not. Okay, so for example, you could give like a mobile agent, you know, the ability to sign on a particular set of messages that satisfy this particular circuit. And the signature will have the property that it looks exactly like a signature by the original signer, which is kind of cool. It's not some, you know, NIZK or, you know, it just really looks exactly like a signature of the original signer. You can also use this for delegation. So if you want some assurance that C of x equals 1, then you can have the cloud produce a signature using this box for you on x. Okay, so what's the scheme? I mean, it's as I said, it's basically the same. The signature is the same as the PRF. You have a verification algorithm here, which uses a one-way function applied to the PRF value. Okay. Which is kind of funny. So how would I verify this? Well, I mean, I get some signature which is purportedly the evaluation of the PPRF at some value. The one-way function is public. I just apply f to it, and I check if it matches the output of that. And it's kind of similar to before. I just pick some random T that's unsatisfying. Okay, and hybrids are a little more involved. So on the left side, I do exactly the same thing I did before. I puncture the PRF key there, and I use the punctured PRF key to sign. On the right side, I puncture the PRF key also, and I hardwire the value that it's supposed to output for that particular T. Okay, so if it gets input T, it just bypasses the evaluation of this function. It just immediately outputs what this value is supposed to be. It's just hard-coded in there. Okay, so that's obviously the same by I/O security, right? Now I just change what's hardwired for T from this value to F evaluated at some random string. So that should be indistinguishable by PPRF security. Now at this point, if the adversary actually forges on T, he's found a preimage of this value, and he's inverted the one-way function, because that's just a random value now. Okay, so if you just go through all the epsilons. Basically, again, you can use complexity leveraging to show that that the signature scheme is secure as long as the security of the PPRF, the I/O scheme, and the one-way function are enough.
So here you're hoping the adversary forge on the point that you punctured?
Yeah, so again, yeah, if you start off in this original case where before I've done all the hybrids, there's nothing about t here, so it's just, there's a 1/2 to the n probability that he's going to pick t to forge on. And then that world is indistinguishable from this world over here where I have all sorts of information hidden, about t.
So do you need sub-exponential security for I/O here?
Yeah. Yeah, so I mean, it's a lot of these things. I'm not really worrying about sub-exponential security of these things. I mean, it's a good problem to get rid of that assumption in all sorts of protocols, but I'm going to be kind of fine with it for this presentation. Okay, so there's thing sort of non-deterministic versions of these things. There's a witness PRF that takes as input, a statement and a witness. It'll output the signature if it's satisfying. And there's sort of the non-deterministic version of signatures, or sort of a Nizic argument that where you get a signature on the value x, assuming this relation is satisfied. So this is statistically zero knowledge because the proof is just a signature on x, a signature on the statement x. It reveals nothing about the witness. Okay, there are lots of papers on constrained PRFs and yes.
Proofs from
Neer and Omer and yeah, a few people have a paper on that. Yes. Okay. All right. So I'll stop here.